What if the most significant structures in the entire universe are not made of matter, but of its near-total absence? We spend our lives adrift in a cosmos that appears, from our terrestrial vantage point, to be a chaotic scattering of brilliant jewels on black velvet. For millennia, we charted these lights, connecting them into heroes and myths, believing them to be the primary actors on the celestial stage, even as our vision deepened, as telescopes resolved faint smudges into island universes, each a swirling metropolis of 100 billion stars. A fundamental assumption remained lodged deep within our cosmic intuition. We imagined a universe that, on the grandest of scales, was essentially uniform, a majestic but fundamentally homogeneous expanse where galaxies were distributed with a kind of gentle randomness, like seeds cast by a divine hand upon the fertile soil of space-time. It was a comfortable thought, a reassuring model of cosmic democracy where every region of space was given a more or less equal share of creation's bounty. This assumption, so elegant and so intuitive, held for generations. It informed our earliest models of the cosmos, providing a stable foundation upon which to build our understanding of universal expansion and cosmic evolution. We saw the universe as a rising loaf of bread, with galaxies like raisins moving apart from one another, but the dough itself was thought to be consistent throughout. To believe otherwise was to suggest a kind of cosmic architecture, a blueprint that implied forces and a history far more complex and far more strangely organised than we had ever dared to imagine. Yet the universe rarely conforms to our comfortable assumptions. It is a place of profound and often unsettling structure, a realm where symmetry is broken on scales that defy human comprehension. The truth of cosmic cartography would not be found by simply cataloguing the lights, but by meticulously measuring their retreat from us, by capturing the subtle shifts in their ancient stellar songs. The key was hidden not just in where the galaxies were, but in how fast they were fleeing. Beginning in the latter half of the 20th century, a new and revolutionary chapter in our exploration of the cosmos began. Astronomers embarked on the monumental task of creating a three-dimensional map of the universe. They did this by patiently measuring the redshift of thousands, and then millions of galaxies. This redshift, a stretching of a galaxy's light towards the red end of the spectrum, is the cosmic yardstick. It is the signature of an expanding universe, telling us with remarkable precision how far away a galaxy is and how swiftly it is receding. For years, data points were collected, catalogued and plotted. Each point was a galaxy, a majestic pinprick of light representing a civilization of stars. And as the map slowly took shape, a picture of reality emerged that was so staggering, so utterly unexpected, that it shattered our old conceptions forever. The universe was not a uniform sea of stars. It was a sponge. It was a neural network. It was an intricate, incandescent web. Stretching across billions of light years, we saw it for the first time, the cosmic web. This is the true architecture of the universe, the grand design sculpted by gravity from the faint quantum whispers of the Big Bang. It is not a universe of scattered islands, but a single, interconnected continent of light and matter. We saw galaxies funneled into immense shimmering filaments, luminous rivers of stars and gas flowing through the dark. These filaments, glowing with the combined light of tens of thousands of galaxies, act as the universe's great interstellar highways, channeling matter from one region to another over cosmic timescales. They are the arteries of the cosmos, pulsing with the raw materials for starbirth and galactic evolution, their gravitational currents guiding the slow, inexorable dance of cosmic assembly. Looking closer, we saw where these brilliant filaments intersected. At these junctions, matter had been accumulating for over 13 billion years, drawn together by an inescapable gravitational pull. Here lie the great clusters and superclusters, the bustling, glittering metropolises of the universe. These are the cosmic cities, dense and ancient realms containing thousands of galaxies locked in a frantic gravitational embrace. They are cauldrons of cosmic violence and spectacular creation, places where galaxies collide and merge, their stellar populations stripped away and flung into intergalactic space. The gas between them glows at millions of degrees, a testament to the immense energy bound within these structures. These clusters are the brightest, most massive and most densely populated regions in the entire cosmos, the shining nodes from which the entire cosmic web seems to emanate. They are the anchors of creation, and connecting these clusters, forming the vast flattened plains of this celestial architecture, are the Great Walls of Galaxies, immense sheet-like structures stretching for hundreds of millions of light-years. They represent some of the largest coherent objects ever discovered. Standing before a map of this structure, you can almost feel the gravitational echoes of its formation, the slow, patient work of an invisible sculptor shaping the universe from the inside out. It is a masterpiece of physics, a testament to the power of gravity acting over unimaginable spans of time and space. For a time, we were mesmerized by this newfound structure. We celebrated the discovery of the filaments, the clusters, and the walls. Our attention was completely captured by the light, by the dazzling concentrations of matter that made up this celestial tapestry. We were, in a sense, like explorers first mapping a new continent, focusing entirely on the mountain ranges and the river systems, charting the places where life and activity were most abundant. But in doing so, we were overlooking the most dominant feature of the map. We were ignoring the vast, dark spaces between the rivers and mountains. For the most startling revelation of the cosmic web was not what it contained, but what it did not. The filaments and clusters, for all their grandeur, make up only a tiny fraction of the volume of the universe. The rest, the overwhelming majority of space, is something else entirely. It is empty. Profoundly, shockingly, almost perfectly empty. These are the cosmic voids. As we charted the glittering highways of the cosmic web, we simultaneously unveiled the colossal deserts that lay between them. These are not simply gaps. They are structures in their own right, defined by an astonishing absence of matter. They are immense, spherical, and bubble-like regions, with diameters stretching from 100 million to over 1 billion light-years. They are the silent, dark counterpoint to the bright, chaotic energy of the superclusters. If a galaxy cluster is a teeming city roaring with the noise of 1 billion suns, then a void is a soundproofed room the size of a solar system. The sheer scale is difficult to internalize. To cross a typical void, a beam of light, the fastest thing in the universe, would need to travel for 300 million years. Our own Milky Way galaxy, a structure we consider vast, would be like a single grain of sand lost in an empty coliseum. The density of matter inside these voids is less than 1/10 of the cosmic average. They are the great whispering vacuums of creation. Imagine for a moment that you could pilot a ship directly into one of these immense chasms. As you leave the bustling outskirts of a galactic filament, the view from your cockpit would begin to change in a way no human has ever experienced. The familiar dense tapestry of galaxies would start to thin out. The great spirals and elliptical cities of stars would recede behind you, their collective light dimming, coalescing into a shimmering wall on one side of the sky. Ahead there would be nothing. A profound and unbroken darkness, deeper than any night sky seen from Earth. For millions of years you would travel, and the view would barely change. The Great Wall of Galaxies behind you would shrink, its light growing fainter and redder, eventually becoming just a faint milky smudge in your rearview mirror. In every other direction, there would be only the cold, distant light of the most ancient, faraway quasars and the faint, uniform hum of the cosmic microwave background radiation. You would be utterly, cosmically alone, more isolated than any human has ever been. In the heart of a great void, the nearest major galaxy might be 50 million light-years away. From such a vantage point, the entire universe would appear as a distant ethereal fog on the horizon. The very concept of night sky, as we know it, would cease to exist. These voids are not just empty spaces, they are active participants in the cosmic drama. Their existence is a powerful confirmation of our theories about dark matter and dark energy. The feeble gravitational pull inside a void is no match for the mysterious repulsive force of dark energy, the engine of cosmic acceleration. The voids are therefore expanding faster than the rest of the universe, pushing the filaments and walls further apart, acting like immense, inflating balloons that dictate the future evolution of the cosmos. They are the arenas where dark energy reigns supreme, the places where the ultimate fate of our universe is being written. They are the quiet, dominant force shaping the grand architecture of reality. They were once considered cosmic wastelands, celestial dead zones unworthy of serious study. But we now understand them to be one of a two-part cosmic ecosystem. Without the voids, there could be no web. Without the darkness, there could be no light. But our exploration of these vast and desolate oceans of quiet would soon reveal something that defied this perfect duality. A discovery that presented a paradox so profound it would force us to question the very foundations of our models of galaxy formation. The deserts, it turned out, were not entirely barren. The cathedrals of silence were not entirely empty. As our surveys became more sensitive, our telescopes peering deeper into the darkness, we began to see them. Faint, lonely smudges of light, adrift in the crushing emptiness. A single, isolated spark where there should have been only shadow. At first, they were dismissed as statistical noise, as errors in the data, or perhaps as foreground objects misidentified and wrongly placed on our three-dimensional map. It seemed impossible. How could a galaxy, a structure that we believed required a dense nursery of gas and dark matter to form, exist here? A galaxy is a product of community, born from the gravitational collapse of enormous clouds of matter, fed by streams of gas flowing along the cosmic web. They grow by consuming their neighbours, by merging and colliding in the chaotic traffic of the galactic filaments. The entire story of galaxy formation, as we understood it, was a story of accumulation, of the rich getting richer in the dense neighbourhoods of the universe. Yet here they were. These are the Void Galaxies, the loneliest objects in the cosmos. They are the ultimate cosmic outliers, the extreme exceptions to the rules of cosmic structure. These are not grand, majestic spirals like our Milky Way, nor are they giant, fiery ellipticals. They tend to be smaller, bluer, and more pristine, rich in the gas that has long been exhausted in their city-dwelling cousins. They are ghostly islands of light in a sea of nearly infinite darkness. Finding one is like finding a single, thriving rose blooming in the centre of the Sahara Desert. Their very existence is a profound and unsettling mystery. They are cosmic castaways, seemingly untethered from the great web of creation that connects all other things, and they pose a series of questions that strike at the heart of our understanding of the universe. Where did they come from? Were they born in the bustling filaments and then somehow ejected, flung out into the desolate wilderness by a violent gravitational interaction, like cosmic refugees exiled from their homeland? The energies required for such an eviction would have to be colossal, a gravitational slingshot of almost unimaginable power. Or, and this is perhaps the more tantalizing and disturbing possibility, did they somehow form right where we see them? Did a tiny, leftover flicker of matter in the primordial universe, a density fluctuation that was almost smoothed out into nothing, somehow manage to cling to its own gravity? Did it patiently and slowly, over 13 billion years of solitude, gather the scarce wisps of hydrogen in its desolate neighbourhood to build itself, star by star, into a functioning galaxy? To form in place would be to defy the odds on a cosmic scale, a quiet miracle of persistence in the most inhospitable environment the universe has to offer. These faint, solitary beacons challenge everything we thought we knew. They are laboratories for studying galaxy formation in its purest form, free from the messy, violent interactions that dominate the lives of galaxies in crowded clusters. They are pristine relics, holding clues to the nature of the early universe, their unperturbed chemistry a snapshot of a bygone era. They may even hold secrets about the nature of dark matter itself, their strange dynamics offering a new window onto this invisible substance. To understand these lonely wanderers is to understand the extremes of cosmic evolution. They are the ultimate test of our theories. They force us to look beyond the bright lights of the cosmic cities and into the vast, quiet heartland of the universe, to confront the possibility that creation happens not only in the fire, but also in the frost. To solve the riddle of the Void Galaxies, we must first journey back to the places they seem to have escaped, the violent, chaotic and spectacular furnaces where the grand majority of galaxies are forged, we must plunge into the heart of the cosmic web itself. What if the most important map ever created was not a map of what is, but a map of what is not? For millennia, we have charted our world by its continents, its mountains, its rivers. We defined ourselves by the land we occupied. When we finally turned our gaze to the heavens, we brought that same terrestrial thinking with us, assuming a universe dotted with brilliant islands of matter adrift in a passive, featureless sea. We were searching for the landmarks, the celestial continents we called galaxies, believing that by connecting these dots we would understand the whole. We could not have been more wrong. The true story of the cosmos, the grand architecture of reality itself, would only be revealed when we finally learned to chart the emptiness, to survey the silences, and to confront the staggering, soul-crushing scale of the abyss. This is the story of that map, and of the lonely inhabitants we discovered living in its most desolate regions. For the first few decades after Edwin Hubble shattered our cosmic solitude, proving that the faint smudges in our telescopes were entire galaxies like our own, our conception of the universe was one of majestic yet simple chaos. It was a cosmos of brilliant islands adrift in an infinite ocean of night. Billions of them, each a swirling metropolis of stars, gas and dust, were thought to be scattered more or less uniformly through space, like sand tossed across a black velvet cloth. The universe was expanding, yes, a discovery that reshaped our understanding of time and origin, but its texture was presumed to be smooth. On the larger scales, we believed, one patch of sky would look much like any other, a democratic distribution of matter across the aeons. This was a comforting, almost elegant idea, a universe that, while immense, was at least predictable in its grandeur. Our view was shaped, as it so often is, by the limits of our tools and the biases of our intentions. Early astronomers were treasure hunters. They aimed their new powerful telescopes at the most promising targets, the brightest jewels in the sky. They sought out the great galactic clusters, like the teeming Virgo and Coma clusters, places where thousands of galaxies were crammed together in a brilliant, violent gravitational dance. These were the cosmic cities, the obvious places to study galactic evolution, stellar birth, and the dramatic lives of celestial objects. Patiently, over long, cold nights, they would expose delicate photographic plates for hours, capturing the faint ancient light from these distant systems. Each plate was a triumph of technology and endurance, a tiny window into the deep past. Measuring the universe in those days was an act of painstaking artisanal science. An astronomer would spend an entire night guiding a telescope to capture the spectrum of a single faint galaxy. That spectrum, a rainbow of light stretched out and dissected, held the key to the cosmos. Within it were dark lines, absorption bands telling of the elements inside the galaxy's stars. But more importantly, those lines were shifted. For distant galaxies, they were almost always shifted towards the red end of the spectrum, the telltale sign of an object moving away from us. This was the cosmic redshift, the echo of the Big Bang's expansion written in light. By measuring the degree of that shift, we could calculate a galaxy's velocity, and through Hubble's law estimate its distance. We were, for the first time, adding depth to our flat portrait of the sky. We were building a three-dimensional map. But the map was being drawn one single laborious point at a time. Decades of this heroic effort yielded a catalogue of a few thousand galaxies, a mere handful of data points against the overwhelming black. And with such sparse information, the assumption of a smooth, uniform universe held firm. It was the simplest explanation, the default state. Why would the cosmos be anything else? Yet, even in this early, pointerless sketch, there were whispers of something more, subtle hints of a grander design that most were not yet equipped to see. Astronomers like Gérard de Vaucouleurs began to notice that the islands were not quite so isolated. Our own Milky Way, it turned out, was not a lone wanderer but part of a small gathering, the local group. And this group was itself being tugged toward the colossal Virgo cluster. De Vaucouleurs took this idea further, painstakingly tracing connections between nearby groups and clusters. He proposed that we lived within a vast, flattened structure, a local supercluster, a continent of galaxies spanning 100 million light-years. It was a controversial idea, flying in the face of the prevailing cosmological principle of uniformity. To many, these superclusters seem like mere statistical flukes, a cosmic version of seeing faces in the clouds. How could we know if this structure was real, or just a local anomaly in an otherwise random universe? The debate raged, but the data was simply too thin. We were like ancient mariners trying to map the world from a single bay, unable to comprehend the continents and oceans that lay beyond our horizon. To see the truth, we wouldn't just need a better telescope. We would need a revolution in how we mapped the heavens. We had to stop hunting for individual treasures and begin a systematic, impartial census of everything. That revolution began not with a bang, but with the quiet hum of new technology. By the late 1970s, digital detectors began to replace photographic plates, and computers could automate the painstaking work of analysing galactic spectra. What once took an entire night for a single galaxy could now be done in mere minutes. The door was swinging open to a new kind of cosmic cartography, one based not on quality, but on quantity. It was an opportunity seized by two astronomers at the Harvard-Smithsonian Center for Astrophysics, Margaret Geller and John Hucra. They were not content with the old biased maps. They wanted to see the real picture, to survey the universe without prejudice. Their goal was audacious, to systematically measure the redshifts of thousands of galaxies in a repeating slice of the sky, like a geologist taking a core sample of the Earth. Their project, the CFA Redshift Survey, was a brute force assault on the unknown. They would point their telescope at a long, thin strip of the northern sky, measure the position and redshift of every galaxy above a certain brightness, and then do it again for the adjacent strip. It was methodical, repetitive, and utterly transformative. They were not just taking a photograph, they were conducting a cosmic census, building a true three-dimensional model of our local universe, one galaxy at a time. As the data began to pour in, they fed it into their computers. Each galaxy became a single point of light, placed in the virtual darkness according to its position on the sky and its distance from us, inferred from its redshift. For the first time, we were about to see a fair and representative slice of the cosmos. No one, not even Geller and Hucra, was prepared for what they found. The old idea of a smooth, uniform universe did not just crumble, it was utterly annihilated. As the points populated the screen, they did not form a random, peppered scattering. Instead, a stunning, unbelievable structure began to emerge from the darkness. It was a universe of majestic patterns, of impossible architecture. Galaxies were not islands. They were strung together like pearls on invisible filaments of gravity. They were clustered into great knots and intersections, and they were spread across vast, flattened sheets that stretched for hundreds of millions of light years. In one of the survey's first slices, a now iconic shape appeared, a crude figure of a person with outstretched arms that astronomers affectionately dubbed the Stick Man. It was a whimsical name for a profound revelation. The universe was not a random scattering of points, it had a skeleton. This was the discovery of the cosmic web, a vast interconnected lacework of matter that pervades all of space, the largest structure in existence. It is the scaffolding upon which the universe is built, a gossamer network spun from gravity and dark matter in the aftermath of the Big Bang. The regions we once called superclusters were revealed to be merely the brightest, densest intersections of this web, the bustling metropolitan hubs where filaments and walls converge. These nodes, like the Coma Cluster, are the cosmic cities, frenetic places where galaxies constantly collide and merge, where the gravitational environment is so extreme it can strip the gas from a galaxy, ending its ability to form new stars. They are brilliant, beautiful, and profoundly violent. Stretching between these great cities are the filaments. These are the cosmic highways, immense tendrils of galaxies and dark matter, flowing like rivers through the intergalactic medium. They channel material from the quieter parts of the universe towards the massive clusters, feeding them, growing them over billions of years. A galaxy living within a filament is on a one-way journey, slowly but inexorably drawn toward the nearest great intersection. its fate sealed by the irresistible pull of gravity. And surrounding these filaments, like colossal curtains hanging in the dark, are the galactic walls or sheets. The most famous of these, the Great Wall discovered by Geller and Hushra, is a staggering structure, a ribbon of thousands of galaxies stretching more than 500 million light-years across space. It was a structure so immense that it defied the cosmological models of the day. For a moment it seemed we had found the ultimate map, the final answer to the universe's floor plan. We saw the cities, the highways, the great walls that defined the cosmic landscape. But in revealing the structure, the CFA survey had uncovered an even deeper and more unsettling mystery. For every dazzling filament and every brilliant wall that appeared on their map, something else appeared with it, the space in between. And this space was not just empty, it was empty. Vast, spherical, impossibly dark regions where the survey found almost nothing at all. These were not mere gaps. They were colossal voids, cosmic deserts hundreds of millions of light-years across, dwarfing the structures that contained them. The discovery of the voids fundamentally changed our perception of our place in the universe. We do not live in a cosmos filled with galaxies. We live on the luminous froth of a universe that is mostly empty. By volume, the voids are the dominant feature of the cosmos. They are the true face of our universe. The filaments and walls of the cosmic web are the exceptions, the glowing threads that outline the immense bubbles of nothingness. Think of it like a sponge. We had spent a century studying the material of the sponge itself, marvelling at its structure, only to finally realise that the holes are vastly larger, that the sponge is mostly whole. These are places of profound silence and primordial solitude. Here, the expansion of the universe proceeds almost unchecked, pushing the few stray inhabitants ever further apart. The gravitational currents that define life in the cosmic web are absent, replaced by a gentle opposing outflow from the void's centre, a cosmic exhalation that ensures its emptiness endures. According to the models of cosmic structure formation, these voids should be almost entirely barren. In the early universe, tiny fluctuations in density acted as seeds for gravity. Regions that were slightly denser than average began to pull in more and more matter, growing into the filaments and clusters we see today. But regions that were slightly less dense than average had the opposite fate. They were left behind, their meagre material stolen away by their voracious neighbours, becoming ever more rarefied as the universe expanded. The voids are the leftover material of creation, the quiet backwaters from which all the action has long since departed. They are the natural, expected consequence of a universe built by gravity. They are supposed to be empty. And yet, as our surveys grew deeper, as our technology became more sensitive, we began to see ghosts in the machine. While the great voids on Geller and Huchra's map were shockingly empty compared to the Great Wall, they weren't absolutely perfectly empty. Here and there, the surveys picked up a faint, lonely point of light, a single galaxy where a cosmic desert should be. At first, they were dismissed as statistical noise, or perhaps foreground objects misidentified and wrongly placed on the three-dimensional map. They had to be errors, because if they were real, if galaxies could truly exist in these vast solitudes, then they posed a profound challenge to our new and beautiful picture of the cosmos. These lone specks defied the relentless logic of gravity. They were survivors in a land of exile, homesteaders in the great cosmic wilderness. What were they? How did they get there? And what could life be like for a galaxy born into the deepest, darkest, loneliest place in the entire universe? And so, with the cosmic map redrawn, with voids carved out of the universe like colossal empty rooms in an infinite mansion, the hunt began. It was a pursuit born not of certainty, but of a tantalizing, almost heretical question. Could anything truly live in the dark? Could life, in its grandest, most galactic sense, take root in these profound solitudes? The first challenge was simply one of perception. Finding a galaxy in the great nothing is not like spotting a ship on a calm sea. It is like searching for a single, unlit candle in a continent-wide cavern during a starless midnight. These hypothetical objects would be, by their very nature, faint, isolated, and utterly overwhelmed by the glare of foreground stars and the sheer, empty distance between us and them. The first dedicated surveys were exercises in extreme patience. Astronomers pointed our most sensitive instruments at the most profound vacancies they could find, opening their shutters for exposures that lasted not minutes, but entire nights, sometimes accumulating light over weeks. It was a vigil measured not in hours, but in years. A collective, patient stare into the darkest corners of the universe, waiting for the faintest whisper of light to betray a presence where none was thought to exist. And then, slowly, pixel by agonizing pixel, the ghosts began to appear. They were not the majestic, pinwheeling spirals of our own cosmic neighbourhood, nor were they the titanic glowing ellipticals that anchor the great clusters. The first Void Galaxies to resolve into focus were underwhelming. They were spectral, wraith-like smudges of light, so dim and diffuse that they seemed on the verge of dissolving back into the blackness from which they had been summoned. These initial discoveries, like the faint outlines of a forgotten civilization, were met with a mixture of triumph and confusion. The triumph was in the confirmation. The voids were not perfectly empty after all. But the confusion was far more profound, for these objects were fundamentally strange. When we measured their properties, they seemed to defy the neat categories we had built for the rest of the cosmos. Their luminosity, the total amount of light they emitted, was astonishingly low. Compared to a galaxy like our Milky Way, a bustling metropolis of hundreds of billions of stars, these were little more than tiny, isolated hamlets, home to perhaps only a few million suns, or even fewer. They were cosmic dwarves, lost in a wilderness designed for giants. Their smallness was not just a matter of star count, but of physical size. They were compact, insular systems, lacking the grand, sweeping arms or the extended halos of gas that characterized their more social cousins. It was as if we had discovered a species of tree that had learned to grow in a vacuum. Everything about them screamed of deprivation. They were starved of gas, the raw fuel for starbirth. They were starved of gravitational encounters, the violent, chaotic mergers and interactions that trigger brilliant bursts of creation in denser environments. They existed in a state of near-perfect isolation, cosmic hermits that may not have interacted with another significant galaxy for billions of years, perhaps for their entire lifetimes. This profound seclusion began to paint a picture of a completely different path of cosmic evolution, a road far less travelled. While galaxies in the cosmic web are constantly jostled, harassed and fed by streams of incoming material, these loners were left utterly to themselves. Their growth was stunted, their development arrested. They were frozen in a juvenile state, like a tadpole that never becomes a frog because the pond it lives in lacks the nutrients for transformation. As our observational techniques improved, as we moved from simply detecting these phantoms to dissecting their light, an even more peculiar story began to unfold. We looked at their colour. In astronomy, colour is not an aesthetic choice. It is a vital diagnostic tool. A galaxy gleaming with brilliant blues and stark whites is a place of turmoil and youth, dominated by massive hot young stars that burn through their fuel with ferocious intensity and die young. A galaxy, glowing in the deep reds and soft oranges of the spectrum, is a far more sedate, ancient place. Its stellar population dominated by old, cool, long-lived stars. It is a galaxy whose glory days of creation are long past. When we looked at the Void Galaxies, we expected to see one or the other. Perhaps they would be ancient and red, relics that formed early and then used up all their fuel, slowly fading into obscurity. Or perhaps, starved of interactions, they might be reservoirs of pristine gas, waiting for some trigger to ignite them, meaning they would be uniformly young and blue. What we found was a perplexing paradox. Many of them were indeed strikingly blue. They were awash with the light of young stars. This was a shock. In an environment so devoid of raw materials and external triggers, how were these galaxies actively building new suns? It was like finding a roaring bonfire in the middle of a barren desert, with no visible source of wood for miles. It suggested that star formation in the voids operates by a different set of rules. Instead of the frantic, merger-driven starbursts that typify galaxy clusters, creation here was a slow, gentle, and perhaps intermittent process. These galaxies were not experiencing a single, explosive baby boom. Instead, their history appeared to be one of small, isolated bursts of activity separated by long, quiet epochs of slumber. A flicker of creation, followed by an eon of quiescence, then another flicker. Their star formation was not a raging fire, but a slow-burning ember, carefully husbanding its meagre fuel supply over the vast timescale of cosmic history. This peculiar, stuttering mode of creation meant they were not just small and faint, but also chemically primitive. Every generation of stars forges heavier elements, the carbon, oxygen, and iron that are essential for planets and for life, and then bequeaths them to the next generation when they die. In the bustling cities of the cosmic web, this process of enrichment happens quickly and repeatedly, but in the voids, with their sporadic bursts of starbirth, the process was incredibly inefficient. When we analysed the light from these galaxies, we found them to be remarkably poor in heavy elements. They were chemically pristine, almost unpolluted by the ashes of previous stellar generations. This discovery was electrifying. It meant that the gas within these galaxies was a close analogue to the primordial gas that filled the universe shortly after the Big Bang. They weren't just isolated in space, they were isolated in time. They were living fossils, pristine relics of an earlier, simpler cosmos, preserved in the sterile, unchanging environment of the void. While the rest of the universe evolved, they remained in a state of suspended animation. Here, in the loneliest places imaginable, we had found a direct window into our own cosmic origins, a chance to study the raw ingredients of galaxy formation in a laboratory untouched by the chaos of the cosmic web. We could study them to understand what a galaxy becomes when it is left entirely alone, a control group for the grand cosmic experiment. Yet for every answer these observations provided, they raised a dozen more unsettling questions. And it was here that the story turned from one of astronomical curiosity into a full-blown scientific confrontation. The problem was not what these galaxies were, but that they were there at all. Their very existence was a direct and uncomfortable challenge to the prevailing cosmological models of the time. Our understanding of how structure forms in the universe, the beautiful and powerful framework known as the lambda cold dark matter model, is built upon a simple, elegant idea. Gravity is the ultimate architect, and gravity in our universe is overwhelmingly dominated by dark matter. This invisible, mysterious substance provides the cosmic scaffolding upon which everything else is built. According to the model, the universe began as a nearly uniform sea of matter and energy, but there were minuscule quantum-scale fluctuations in density. Over eons, gravity amplified these tiny seeds. Regions that were slightly denser than average attracted more and more material, growing into the vast halos of dark matter that would eventually host galaxies and clusters. Regions that were slightly less dense gave up their material, emptying out to become the voids. The model was a story of the rich getting richer and the poor getting poorer. The filaments and clusters of the cosmic web are the places where dark matter collected, creating deep gravitational wells. These wells acted as cosmic basins, funneling in pristine hydrogen and helium gas from their surroundings. It was only inside these deep dark matter wells that the gas could become dense enough to collapse under its own weight, to cool and to ignite the first generations of stars. The model's prediction for the voids was therefore stark and unambiguous. They should be empty. Not just mostly empty of galaxies, but almost completely devoid of the dark matter scaffolding necessary to build them in the first place. The gravitational terrain of a void is not a well, but a gentle sloping hill. Any small clump of dark matter that happened to find itself there should be gravitationally repelled, pushed outwards towards the massive walls of the surrounding superclusters. Any gas in a void would be too diffuse, too thinly spread to ever reach the critical density needed for collapse. To form a galaxy, you need a seed, a significant clump of dark matter to act as a gravitational anchor. The voids, by their very definition, were the places where those seeds had been systematically weeded out by cosmic evolution. So, the faint smudges of light we were finding were more than just curiosities. They were cosmological heresy. They were impossible objects, structures that our best and most successful theory of the universe said should not exist. A few might be explained away as statistical flukes, perhaps small galaxies that formed in the filaments, and were later ejected into the void by some violent gravitational interaction, like a cosmic slingshot. But the numbers we were starting to find seemed too high for that explanation, and their pristine, underdeveloped nature suggested they were not exiles, but natives. They seemed to have been born in the emptiness, an act of creation that our physics could not readily explain. This was not a minor discrepancy, a small detail to be ironed out. It was a crack in the very foundation of our understanding. The confrontation was direct. On one side, you had the elegant predictive power of the cosmological models, which had successfully explained the large-scale structure of the universe, the cosmic microwave background, and the formation of massive galaxy clusters with breathtaking accuracy. On the other side, you had these stubborn, faint points of light, quietly testifying to a reality that was more complex, more nuanced, and far stranger than our theories had allowed. They represented a fundamental tension between observation and theory. Were the models wrong? Or at least incomplete? Had we missed a crucial piece of the puzzle, some unknown mechanism that could allow for genesis in these gravitational deserts? The scientific community was split. For theorists, these void galaxies were a nuisance, a messy complication that disrupted the clean lines of their simulations. Their simulations, which could beautifully recreate the cosmic web, consistently produced voids that were far emptier than what the observers were now finding. To them, the challenge was to figure out how their models could be tweaked. Perhaps the initial seeds of structure were not distributed quite as they had imagined. Maybe some low-mass dark matter halos could, against all odds, survive and even grow within the hostile environment of the void, capturing just enough gas over billions of years to ignite a tiny, flickering galaxy. It was a search for a loophole in the laws of cosmic construction. For observers, however, these galaxies were a treasure. They were a sign that the universe still held deep secrets, that our map of reality was still a work in progress. They pushed astronomers to develop new techniques, to build more powerful telescopes capable of capturing ever fainter light, to probe these ghostly systems in more and more detail. Each new void galaxy discovered was another piece of evidence laid at the feet of the theorists, another quiet insistence that the story of the cosmos was not yet fully written. The confrontation was not hostile, but it was profound. It was the engine of scientific progress, the friction between what we think we know and what the universe actually shows us. These lonely, underdeveloped galaxies existing where they had no right to be had become the unlikely vanguard of a cosmological revolution. They forced us to look back at our most cherished theories and ask a difficult, humbling question. How did they get there? Were they truly born in the void, a testament to a mode of galaxy formation we'd never imagined? Or were they cosmic castaways, thrown out from the bustling filaments in some ancient, violent event, forever exiled to wander the great dark? Answering this would require more than just pictures. It would demand a new kind of cosmic archaeology, a way to read the life stories of these galaxies and trace their journeys across the eons. The impossible fact of their existence had opened the door. Now we had to have the courage to step through it, to follow the evidence into the heart of the emptiness and uncover the secrets it held. The quiet rebellion of the void galaxies was just beginning. For a time, the paradox felt absolute, a cosmic contradiction etched into the very fabric of the universe. Our models, so elegant and so powerful, had painted a masterpiece of cosmic evolution, where the rich grew richer and the poor were left with nothing. They predicted gravity's inexorable pull, a force that shepherds matter into glorious filaments and magnificent superclusters, leaving behind only an abyss, profound and empty. And yet, against that backdrop of predicted nothingness, the stubborn reality of the void galaxies persisted. Faint, defiant sparks in the deepest darkness, they were ghosts in a machine that swore ghosts could not exist. The dissonance in our cosmic symphony was deafening. It forced upon us a question that cut to the very core of our understanding. Was our grand theory of cosmic evolution fundamentally, catastrophically flawed? Or was the hidden story of these lonely wanderers simply more complex, more violent, and far more beautiful than we had ever dared to imagine? The answer, when it began to emerge, came not from a telescope's lens, but from the glowing heart of a supercomputer. Science often progresses not with a single eureka moment, but with a slow, grinding increase in power. For decades, our cosmological simulations were like painting a continent with a housebrush. We could capture the broad strokes with stunning accuracy, the shape of the continents, the placement of mountain ranges. We could render the cosmic web, but we lacked the fine-tipped brush needed to paint the individual trees, the hidden streams, the secluded valleys. Our digital universes were too coarse, their fundamental pixels of matter too large, to properly resolve the delicate lives of dwarf galaxies, let alone those adrift in the voids. These lonely systems were simply too small, too tenuous, their formation too subtle a process to be captured by the computational brute force of the era. They fell through the cracks of our digital nets, lost in the rounding errors of our cosmic calculus. But a revolution was quietly brewing, a surge in computational power that would change everything. We were about to trade our house brushes for microscopic needles. The new generation of simulations, programs with names like Illustra's Eagle and Bolshoi, were not merely upgrades, they were entirely new kinds of digital cosmos. Running on world-spanning networks of processors, these behemoths consumed electricity by the megawatt and ran for months on end to simulate a sliver of cosmic time. Inside their silicon minds, billions of light-years of virtual space could be rendered with breathtaking fidelity. For the first time, we could create universes in a box where we didn't just track the gravitational clumping of dark matter. We could now include the complex, messy, and crucial physics of ordinary matter. We could simulate the way gas cools and swirls, the way radiation from the first stars blasts through interstellar clouds, the way supernovae explode and enrich their surroundings with heavy elements. We were no longer just sketching the skeleton of the cosmos. We were finally rendering its flesh, its blood, its breath. We were building digital universes so rich, so detailed, that we could fly through them, zoom in on a single filament and watch, as if gods, the birth of a single tiny galaxy. And it was in the silent, dark regions of these new digital cosmos, the places our older models had rendered as sterile voids, that something extraordinary began to happen. Out of the simulated vacuum, against all previous expectation, galaxies started to form. They were not grand spirals or luminous ellipticals. They were faint, fragile wisps of stars and gas, emerging hesitantly from the background hum of the universe. For the theorists who had spent years staring at the paradox, this was a moment of profound revelation. The problem wasn't a crack in the foundations of physics. The problem was that we had been asking the wrong question. We had asked, why is there something where there should be nothing? The simulations, in their silent numerical wisdom, offered a new perspective, suggesting the question should have been, what kind of something can survive, or even thrive, where almost nothing exists? From the churning data of these virtual realities, two astonishing competing narratives for the origin of void galaxies began to crystallize. Two possible lives for these celestial hermits. The first story is one of patience. A tale of cosmic late bloomers. In this scenario, a void galaxy is not an interloper, but a native of the emptiness. Imagine a region of the early universe, a patch of space only marginally denser than the near-perfect vacuum surrounding it. In the great gravitational land rush of the cosmos, this was the unwanted territory. While its neighbours were pulled into the frantic construction of galactic cities and superhighways, this tiny, forgotten wisp of hydrogen and helium was left behind. For billions of years, it did almost nothing. Gravity's voice here was not a command, but a whisper. The process of collapse, which happened in a cosmic blink of an eye in denser regions, was here stretched over an almost eternal timescale. It was a slow, deliberate gathering of self. For an eon, it was little more than a phantom cloud, a ghost of a galaxy to be, its potential locked away in the cold and the dark. Then, slowly, painstakingly, the centre began to cool and condense. The first few stars flickered into life, not in a brilliant burst, but as lonely scattered points of light. These are the quiet ones, the galaxies that took the slow road, forming in profound isolation, shaped only by their own fragile gravity and the patient passage of cosmic time. They are, in a sense, pristine fossils, holding a chemical memory of a universe less touched by the chaotic recycling of matter that defines their city-dwelling cousins. This theory was elegant, simple, and it explained so much about their underdeveloped nature. But the simulations had another, more violent story to tell. The second narrative is not one of patience, but of exile. It is a story of survival. In this dramatic telling, a void galaxy is a castaway, a refugee flung from the chaos of its birthplace. Picture a young, small galaxy, born not in the quiet of the void, but in the bustling suburbs of a galactic group. Its life is precarious, dominated by the gravitational whims of its much larger neighbours. It's caught in a cosmic dance with 2 or 3 massive galaxies, a gravitational waltz where the partners are titans and it is merely a feather. As these giants swing past one another, their immense gravitational fields warp and twist the space around them. Our small galaxy, caught in the wrong place at the wrong time, is snagged by this immense invisible machinery. It is accelerated, pulled, and then, in a final cataclysmic interaction, it is launched. It becomes a projectile fired by a gravitational slingshot of unimaginable power. It is ejected from its home, propelled at hundreds of kilometers per second away from the cosmic filament it once called home. It rockets out into the abyss, a tiny, screaming cannonball of stars and gas, trailing its past behind it. Its journey is a lonely one, across millions of light years of utter blackness. Eventually, its momentum spent, it slows and settles, a solitary wanderer in a land that was never meant to be its own. This theory, the cosmic exile model, was a shocking and beautiful piece of celestial mechanics, and it too explained many of the observed properties. A galaxy ripped from its moorings might have its gas stripped away, stunting its growth and leaving it small and faint just as we see. Suddenly, we had not one, but 2 plausible, compelling, and radically different explanations for the universe's loneliest objects. Were they quiet natives, born of the void's patience, or were they traumatized exiles, born of cosmic violence? The digital universes had given us the questions, but they couldn't give us the final answer. To distinguish between these 2 fates, the patient versus the violent, we needed more than simulations. We needed a perfect test case. We needed to find a galaxy so extreme in its isolation, so utterly and completely alone, that its very existence would push our new theories to their breaking point. We needed to find the ultimate hermit, the king of the void. And so, astronomers turned their gaze back to the sky, sifting through vast digital surveys not for bright, obvious targets, but for the faintest possible whispers from the abyss. The hunt was on. The search was an exercise in technological artistry and human persistence. You cannot simply point a telescope into a dark patch of sky and hope to find a void galaxy. They are too faint, too diffuse, often outshone by a single foreground star from our own Milky Way. The new strategy was to look for their shadows, for their faintest elemental signature. Astronomers scanned the heavens with radio telescopes, vast arrays of dishes tuned to a specific wavelength of light. The 21-centimeter line, the telltale hum of cold, neutral hydrogen gas. This is the raw fuel of creation, the stuff from which stars are made. The idea was to sweep through the enormous voids mapped by galaxy surveys, listening for a tiny, anomalous spike in this hydrogen signal, a blip of gas where there should be only static. It was like trying to hear a single, softly spoken word in a library the size of a solar system. For years, teams of researchers meticulously filtered petabytes of data, chasing down false signals and faint interference, patiently mapping the true emptiness of the cosmos. And then, in a swath of sky in the constellation of Eridanus, they heard it. A whisper. It was a signal so faint it was barely distinguishable from the background noise of the universe. At first, it was dismissed as an error, a glitch in the instruments, but follow-up observations with other radio telescopes confirmed it. There was a cloud of hydrogen gas out there, hundreds of millions of light years away, sitting squarely in the middle of one of the largest, emptiest voids known to science. The next step was a desperate one, to see if this gas cloud had any stars. This required an immense amount of time on one of the world's largest optical telescopes, pointing it at a single, dark coordinate in the sky for hours upon hours, letting photons from this impossibly distant object collect one by one, like raindrops in a thimble. As the image slowly built up on the detector, after countless hours of painstaking observation and data processing, a form began to emerge from the digital noise. It was a smudge. A pale, ethereal, and unbelievably faint collection of stars, so ghostly it seemed on the verge of dissolving back into the black. They called it Seco 1, though some astronomers began to refer to it simply as the Eridanus ghost. It was, and remains, the most extreme example of a void galaxy ever found. Its loneliness is difficult to comprehend. The nearest significant galaxy to it is over 100 million light-years away. If our Milky Way were sitting at its location, our night sky would be almost perfectly black. From the Eridanus ghost, the grand swirl of Andromeda, our nearest major galactic neighbour, would be completely invisible even to the most powerful telescopes on Earth. The entire local group of galaxies would be a barely detectable speck. It is an object defined by an absence of neighbours, a galaxy whose horizon is almost pure, undiluted cosmos. Its discovery was the turning point. This was no longer a curious anomaly or a statistical quirk. This was a profound statement from the universe. The Eridanus ghost, and others like it that were soon discovered, were not just a footnote in the story of structure formation, they were a critical chapter. They were a distinct, albeit vanishingly rare, class of cosmic object. The properties of the ghost were just as stunning as its location. It was a mess. Unlike the small, orderly dwarf galaxies found near the Milky Way, it was chaotic and misshapen. But its most shocking feature was its composition. When astronomers analysed its faint light, they found it was incredibly poor in heavy elements, or metals, as they call anything heavier than helium. In most galaxies, generations of stars have lived and died, exploding as supernovae and seeding their surroundings with the carbon, oxygen and iron necessary for planets and for life. This cosmic recycling enriches a galaxy over time, but the Eridanus ghost seemed to have undergone almost none of this. Its gas was nearly pristine, a chemical fossil from the dawn of time. It was a baby, an infant galaxy that, for some reason, had only just begun the process of star formation in earnest. It was a living relic of the early universe, surviving somehow into the present day. This single, ghostly object solidified everything. It proved that void galaxies were not just a theoretical possibility churned out by a supercomputer. They were a tangible, physical reality that we could study. And in its extreme nature, the Eridanus ghost provided the perfect crucible to test our burgeoning theories. Its pristine chemical nature seemed to scream late bloomer, a native of the void that had only just awakened from a 13-billion-year slumber. Yet its disturbed, chaotic shape hinted at something more violent, perhaps the lingering trauma of a cataclysmic ejection that had flung it into its lonely exile billions of years ago. The contradiction was tantalizing. The evidence pointed in two different directions at once. The universe, it seemed, was not going to give up its secrets easily. The discovery of this ultimate ghost, this lonely king, did not end the mystery. It deepened it, refined it, and gave us the ultimate tool with which to finally solve it. The stage was now set for a direct confrontation between our two great origin stories, a cosmic detective case with a single spectral smudge of light as the star witness, and its testimony, written in the language of starlight and motion, would tell us not only about its own past, but about the hidden dynamics of the entire cosmos. And so, the phantom becomes flesh. The statistical anomaly, once a ghost in our cosmological models, solidifies into a legitimate, bewildering population of galaxies. To accept their existence is one thing. To understand it is a challenge of an entirely different order. The discovery did not solve a mystery. It shattered a comfortable assumption, opening a chasm of new, more profound questions that strike at the very heart of how we believe the universe assembled itself. For every lonely galaxy confirmed, a dozen theoretical complications bloom in its wake. The grand, elegant tapestry of the cosmic web, with its shimmering filaments and dense jeweled intersections, suddenly has threads that lead to nowhere. These isolated worlds are not just unusual, they feel fundamentally paradoxical, an affront to the gravitational logic that governs the cosmos. Their presence forces us to confront an uncomfortable truth. Our map of the universe, as detailed as it has become, may be missing entire continents of possibility, entire modes of cosmic existence we had prematurely dismissed. The question is no longer if they are real, but how. How, in a universe driven by the relentless pull of gravity, a process that herds matter into great cosmic cities, can these hermits possibly endure? How do they come to be, and what does their lonely life story tell us about the cosmos and our place within it? The search for an answer fractures the astronomical community into competing camps, each championing a narrative as different as a quiet birth from a violent exile. The first, and perhaps most elegant of these hypotheses, posits that void galaxies are primordial relics, cosmic fossils left over from the universe's infancy. This idea suggests they were not moved into the voids, but were simply born there, against all odds. To grasp this, you must travel back with us, to a time before stars or galaxies, when the universe was an almost perfectly smooth, hot, dense soup of particles and energy. Almost, but not quite. Quantum fluctuations in that primordial state had sprinkled it with minuscule variations in density, seeds of all future structure. Over hundreds of millions of years, gravity went to work on these seeds. Regions that were infinitesimally denser than their surroundings began to pull in more matter, a cosmic snowball effect that would eventually grow into the great clusters and superclusters we see today. The underdense regions, in turn, were evacuated, their matter siphoned away to feed their voracious neighbours, stretching and expanding to become the colossal voids. According to the relic hypothesis, some of those initial density seeds, even within the regions destined for emptiness, were just barely substantial enough to defy the cosmic exodus. They were like stubborn homesteaders on a frontier that everyone else was abandoning. While the great migration of matter flowed outwards towards the glowing filaments, these small, self-contained pockets of gas and dark matter held their ground. They possessed just enough gravitational authority to collapse in on themselves, to ignite their first generation of stars, and to become a self-sustaining island in an emptying ocean. If this is true, then a void galaxy is something truly precious. A sample of the universe in its purest form. Its entire existence has been a story of serene isolation. It has never known the trauma of a galactic merger, a cataclysmic collision that rips star systems apart and funnels fresh gas into a frenzy of starbirth. It has never been harassed by a larger neighbour, its delicate outer arms stripped away by tidal forces. It has never flown through the hot, dense gas of a galaxy cluster, a celestial blowtorch that scours a galaxy clean of the very fuel it needs to build new stars. This shielded existence makes it a perfect cosmic laboratory, a control group for the grand experiment of galaxy evolution. By studying its properties, its rate of star formation, the chemical composition of its stars, the shape of its structure, we can see what a galaxy would have become if left entirely to its own devices. We can finally disentangle the effects of nature versus nurture on a galactic scale. The galaxies in our own local group, the Milky Way and Andromeda included, are products of a violent, crowded history. Their stories are written in streams of stolen stars and the scars of past collisions. But a primordial void galaxy would be a clean slate, its history written only by its own internal processes. Finding and studying such an object would be like an archaeologist discovering a perfectly preserved settlement, untouched by war, invasion, or even trade, offering an uncorrupted window into a lost way of life. It's a tantalizingly beautiful idea, a narrative of quiet endurance against the grand, chaotic flow of the cosmos. It suggests that even in the most desolate corners of the universe, life, in the form of stellar creation, can find a way. But a second, far more dramatic hypothesis paints a completely different picture. This theory argues that void galaxies are not serene natives but cosmic exiles, violently ejected from the very crowded regions they now avoid. They are not hermits, they are refugees. This is the void drifter model, and its story begins not in the quiet stillness of an embryonic void, but in the chaotic heart of a dense young galaxy cluster. Here, gravity is not a gentle, constructive force, but a brutal, unpredictable tyrant. In these cosmic mosh pits, galaxies are constantly interacting. Imagine a small dwarf galaxy, like so many we see today, orbiting a much larger companion. Now introduce a third, massive galaxy into the dance. The gravitational choreography becomes impossibly complex and unstable. For a brief, terrifying moment, the three bodies engage in a gravitational slingshot. Just as a planet can steal momentum from Jupiter to fling a spacecraft to the outer solar system, a massive galaxy can impart a colossal impulse of kinetic energy to a smaller one. The result is a hypervelocity ejection. The small galaxy is thrown outwards with breathtaking speed, shot like a cannonball from the heart of the cluster. It would travel at hundreds, perhaps thousands of kilometers per second, an impossible velocity for a normal galaxy. It would be moving so fast that the gravitational pull of its home cluster, of the entire cosmic filament it belonged to, could not hold it back. It would escape, crossing the gravitational watershed and coasting out into the vast empty territory of a neighbouring void. It would spend billions of years on this lonely journey, a silent ship sailing an endless sea, its propulsive burn long since finished. If this is the case, then the void galaxies we see are not pristine relics at all. They are survivors of a traumatic event. They would carry the scars of their violent departure. We might expect to see signs of tidal stripping, where the gravitational encounter that ejected them also tore away their outermost stars, leaving them looking truncated and battered. Their internal star motions might be in disarray, still ringing from the gravitational shock. And crucially, their trajectory would tell the tale. A true primordial relic should be more or less at rest within its void, or moving slowly with the overall expansion of the universe. But an ejected galaxy would be a bullet still streaking away from the scene of the crime. Measuring this motion, its peculiar velocity, is a key test to distinguish between these two origin stories. Furthermore, its chemical makeup might betray its urban origins. Galaxies and clusters are often enriched with heavier elements, forged in the hearts of multiple generations of massive stars and spread through the cluster by supernova winds. A void drifter might carry this chemical signature with it, a kind of cosmic accent that reveals it isn't from around here. This hypothesis transforms the narrative from one of peaceful isolation to one of high-speed drama and survival. It populates the voids not with gentle natives, but with the displaced and the exiled galactic flotsam thrown out from the chaotic storms of cosmic structure formation. It implies the voids are not just empty, but are also the destination for the universe's fastest-moving castaways. The universe, in this telling, is a place of such violence that it can unmoor an entire galaxy and banish it to a billion-year solitude. Then there is a third, more nuanced possibility, which weaves together threads of the other two. It isn't strictly about origin, but about the profound consequences of a life lived in seclusion. This view suggests that regardless of whether a void galaxy was born in place or arrived later, its evolution is fundamentally different. It represents a unique and separate pathway for galactic development. In the crowded highways of the cosmic web, a galaxy's growth is constantly being influenced by external factors. A steady stream of cold gas flowing along a filament can provide a continuous supply of fuel for star formation, keeping a galaxy vibrant and blue. A close pass by another galaxy can trigger a dazzling starburst, compressing gas clouds and igniting millions of new stars at once. These are the dynamic, interactive processes that forge the grand spiral and massive elliptical galaxies that dominate the cosmic census. But a void galaxy is cut off from all of this. It is a closed system, a self-contained ecosystem that must live off its own initial inheritance of gas and dark matter. It is shielded from the chaos, but it is also starved of the resources that drive spectacular growth. Its star formation would likely be a slow, steady, continuous process, rather than the boom and bust cycles seen in its filament-bound cousins. Without fresh infusions of gas, it would gradually wind down, slowly consuming its reservoir of fuel over an immense timescale. Its evolution would be a slow, graceful fade rather than a series of brilliant, violent transformations. This shielded evolution model presents void galaxies as the ultimate cosmic time capsules. Because they are not being replenished or disturbed, the stars within them offer a clearer, more unadulterated record of the galaxy's entire history. The oldest stars would be pristine relics of the early universe, their chemical composition untainted by material dredged up in galactic mergers. We could read the layers of its stellar populations like the rings of a tree, each generation telling a simple, clear story of its birth conditions. This makes them invaluable. To understand the complex role of environment in shaping galaxies, we desperately need a baseline, a control group. Void Galaxies are that control group. By comparing their simple, self-contained evolution to the messy, complicated lives of their urban counterparts, we can finally isolate and quantify the precise effects of mergers, gas accretion, and harassment. They are the silent witnesses whose quiet testimony could unlock the secrets of the most spectacular events in the cosmos. These competing narratives, the primordial relic, the cosmic exile, the shielded garden, are not just abstract stories. They are testable scientific hypotheses. But testing them requires pushing the limits of our observational capabilities to their absolute breaking point. The fundamental challenge is one of light and distance. By their very nature, void galaxies are often small, faint dwarf systems, and they reside in the darkest, most distant corners of the cosmos. Finding them is like trying to spot a single, dimly lit fishing boat in the middle of the Pacific Ocean at midnight from a satellite in high orbit. The first hurdle is simply knowing where to look. You cannot simply point a telescope at a patch of sky that appears black and hope to find one. Emptiness in a two-dimensional image is an illusion. That patch could be empty, or it could be aligned with a dense filament of galaxies stretching away from us for 1 billion light-years, just out of view. To find a true void, you need a three-dimensional map. This is where massive brute force sky surveys come into play. Projects like the Sloan Digital Sky Survey, and more recently the Dark Energy Spectroscopic Instrument, or DISI, are heroic feats of cosmic cartography. Over years, they painstakingly measure the positions and distances via redshift of millions upon millions of galaxies. They aren't looking for void galaxies themselves. They are building the framework, mapping the filaments and walls of the cosmic web in breathtaking detail. Only once this 3D map is constructed can astronomers identify the great voids that lie between the structures. The survey data becomes a treasure map, with the empty spaces marked X. Then, and only then, can the real hunt begin. Astronomers deploy sophisticated computer algorithms to sift through the petabytes of data from these surveys, searching for the faintest smudges of light that fall squarely within the geometric boundaries of a confirmed void. It is a search for a needle not in a haystack, but in a field of haystacks, each the size of a continent. Once a candidate is identified, the truly difficult work starts. This is where the world's most powerful telescopes are brought to bear. A team might win precious hours of observation time on the Hubble Space Telescope to get a clear, high-resolution image, to see if the candidate has a discernible shape or structure. Or they might use the giant mirrors of the Keck Observatory or the Very Large Telescope to perform the painstaking task of spectroscopy. This involves capturing the galaxy's feeble light and spreading it out into its constituent colours, a rainbow called a spectrum. Within this spectrum lie dark lines, absorption features that are the chemical fingerprints of the stars within. From these fingerprints, astronomers can deduce the galaxy's chemical maturity, its star formation history, and most importantly, they can confirm its redshift with pinpoint accuracy. This final step is non-negotiable. It is the only way to be absolutely certain that the galaxy is not a foreground or background object, but that it truly resides in the heart of the void. Each successful observation is a triumph of ingenuity and persistence, a testament to the human drive to illuminate the darkest corners of our universe. The challenges are immense, the required precision is staggering, and the objects of study are the faintest things we have ever tried to characterize. Yet, for every new candidate confirmed, we are handed another piece of a grand cosmic puzzle. Each photon of light, gathered after a journey of hundreds of millions of years from one of these lonely worlds, carries with it a clue. It might be a clue about the pristine conditions of the early universe, a clue about the awesome power of gravitational encounters, or a clue about the quiet, uninterrupted life of a galaxy left alone. The debate rages on, fueled by the trickle of data we manage to extract from these cosmic ghosts. The void is no longer just a backdrop. It is a stage for a profound scientific drama. And as our technology sharpens and our maps grow more complete, We are beginning to read the stories written in these isolated points of light, preparing to answer the ultimate question: what secrets have they been keeping out there in the great silent dark? And so the hunt was on. No longer a haphazard search for a few strange anomalies, but a systematic all-sky quest to bring the universe's loneliest residents out from the shadows. The challenge had always been one of sheer, overwhelming scale. Finding a void galaxy was like trying to hear a single, softly spoken word in the deafening roar of a global stadium. The light of billions of galaxies clustered into colossal superstructures drowned out the faint whispers from the great empty deserts in between. For decades, our maps of the cosmos were fundamentally biased, drawn by the brightest lights, the most crowded cities. We had mapped the continents of creation, but the vast oceans of quietude remained almost entirely uncharted territory, their hidden islands unknown. Then came a revolution, a change in perspective so profound it was akin to inventing the globe after centuries of flat maps. It wasn't born from a single telescope, but from a new philosophy of seeing. The era of the great cosmic surveys, projects like the Sloan Digital Sky Survey and later the Galaxy and Mass Assembly Survey, were not designed to stare intently at one small patch of sky. Their goal was titanic in its ambition: to create the definitive census of the local universe, to measure and catalogue the position, brightness, and nature of millions upon millions of galaxies. For the first time, we were not just stargazing. We were engaging in cosmic cartography on an industrial scale, creating a three-dimensional atlas of the cosmos with breathtaking precision. These automated sentinels of the sky worked tirelessly, night after night, methodically scanning immense swathes of the heavens. Their digital eyes, far more sensitive and patient than any human observer, built up a pointillist masterpiece of the universe, one galaxy, one data point, at a time. As this colossal digital tapestry took shape, the grand architecture of the universe leapt into focus with shocking clarity. The filaments, the walls, the great clusters, they were all there, more vibrant than ever imagined. But now, crucially, so were the voids. We could finally delineate their borders, measure their staggering volumes, and, most importantly, systematically sift through their dark interiors for the faint smudges of light we had long been searching for. The age of anecdotal evidence was over. The era of cosmic statistics had begun. With databases containing hundreds of thousands, then millions of galaxies, each with a precise redshift measurement giving us its distance, we could fly through this virtual universe on a computer. We could command the simulation to strip away the bright filaments, to render the crowded clusters invisible, leaving only those objects that inhabited the deepest, most underdense regions. And as the cosmic noise faded, they began to appear. First a dozen, then 100, then thousands. The loners, the exiles, the castaways of the cosmos finally had their moment in the scientific spotlight. No longer mere curiosities, they were now a certified class of cosmic citizen, a population with its own unique demographics, its own story to tell. With this treasure trove of data, we could finally move beyond the what and where and begin to answer the most profound question of all: why? Why do these galaxies exist in such profound isolation? How, in the violent formative eons of the universe, did they manage to escape the inexorable gravitational pull of the cosmic web? The answer, pieced together from sophisticated computer simulations and the fossil record written in the starlight of these galaxies, is a story of chance, timing, and a gentle cosmic nudge at the dawn of time. Imagine the newborn universe, a mere few 100 million years after the Big Bang. It is not the structured cosmos we see today. Instead, it's a seething fog of hydrogen and helium, threaded with invisible tendrils of dark matter, the scaffolding upon which everything will be built. Gravity is the master architect, relentlessly pulling this material into the densest regions of the web. Matter flows along these dark matter filaments like water rushing down 1,000 rivers, all converging toward the great basins that will one day become galactic clusters. Within these cosmic rivers, countless tiny protogalaxies are beginning to form, small fragile whirlpools in the torrential current. For the vast majority of these nascent galaxies, their fate is sealed. They are swept along with the flow, destined to merge, to collide, to be consumed in the gravitational maelstrom of the forming clusters, becoming just one brick in the wall of a cosmic megalopolis. But our simulations revealed something else, a subtle and beautiful exception to the rule. Not every whirlpool is caught in the strongest part of the current. Some, by a simple accident of their birth location, form near the edge of a filament, where the gravitational pull is weaker. Others might be born with a slightly higher initial velocity, a little extra momentum left over from the inflationary kick of the Big Bang itself. For these few lucky proto-galaxies, this tiny initial advantage makes all the difference. Instead of being pulled deeper into the filament, they are gently but firmly pushed outwards, away from the cosmic river. They are the filament escapees. Like a seed pod carried on a faint breeze away from the dense forest, they drift away from the highway of galactic traffic and into the vast open plains of the forming voids. This is not a violent ejection, not a cataclysmic explosion. It is a quiet, almost imperceptible parting of ways, a gravitational slingshot powered not by immense force, but by a precise and delicate imbalance of forces at a critical moment in time. The simulations show this process in stunning detail. We can watch as a small clump of dark matter, destined to become a void galaxy, just misses the on-ramp to a major filament. It skirts the edge of the great gravitational watershed and begins a long, slow journey into the deepening basin of a void. This origin story elegantly explains their most defining characteristics. It explains why they're almost always small dwarf galaxies. Only the low-mass proto-galaxies had a small enough gravitational profile to be nudged off course. The cosmic heavyweights were too anchored by gravity to escape. It also explains why they're so rich in pristine gas. They left the crowded suburbs of the universe before the era of violent stripping and galactic harassment truly began. They departed for their life of solitude with their inheritance of primordial hydrogen and helium almost entirely intact. Their formation, then, was an act of cosmic escapology, but this only solved half the puzzle. How did they then survive for the next 13 billion years? A lone ship on a calm sea may be safe, but it is also cut off from supplies. Without the constant influx of gas from mergers and galactic accretion that fuels their city-dwelling cousins, shouldn't these void galaxies have quickly used up their initial fuel reserves and faded into darkness? Shouldn't they be ancient red and dead relics, galactic ghosts haunting the emptiness? This was the persistent paradox. Yet when our new, powerful telescopes finally got a clear look at them, they revealed the opposite. Many void galaxies are vibrantly, defiantly blue. Blue is the colour of youth in the cosmos, the telltale signature of massive, hot newborn stars. Their presence means that star formation is not just a distant memory for these galaxies, it is an ongoing, active process. They are not ghosts, they are very much alive. The solution to this beautiful mystery lies in the nature of the void itself. We once thought of the voids as being truly, absolutely empty. We now know this is an exaggeration. They are not a perfect vacuum, they are merely extraordinarily underdense. A faint, incredibly tenuous mist of primordial gas. The leftover breath of the Big Bang still permeates these immense regions. For a massive galaxy in a cluster, this thin gruel is utterly insignificant, like a whale trying to survive by breathing fog. But for a small dwarf galaxy, living a slow and quiet life, this cosmic mist is everything. This is the modern theory of cold mode accretion, a process that is gentle, subtle, and almost impossible to observe directly in the chaos of a galaxy group. But in the profound silence of the void, it becomes the dominant source of life. Imagine a lone desert plant. It cannot rely on torrential monsoons for water. Instead, it survives by slowly, patiently drawing in the sparse moisture from the morning dew and the humid night air. This is how a void galaxy lives. It doesn't experience the cataclysmic downpour of a gas-rich merger. Instead, its gravitational field acts like a vast, gentle basin, slowly, patiently, over billions of years, collecting the cosmic dew of the intergalactic medium. These are not dramatic filaments of gas being funneled in, but a slow, steady, almost imperceptible rain of individual hydrogen atoms settling onto the galaxy's disk. This process is incredibly inefficient, but it is also incredibly persistent. It provides a tiny but continuous trickle of fresh fuel, just enough to sustain a slow, burning, stable rate of star formation across cosmic time. This is why their lives are so different. A galaxy like our own Milky Way has a dramatic, violent history. Its biography is written in chapters of chaotic mergers, bursts of frantic star formation, and long periods of recovery. The biography of a void galaxy, in contrast, is a single, continuous, unbroken narrative of tranquility. A slow, steady pulse of creation, beating consistently for 13 billion years. Its isolation is not a curse, it is its shield. Protected from the gravitational bullying of larger neighbours, safe from the tidal forces that would rip it apart, and insulated from the ram pressure stripping that would scour away its gas, the Void Galaxy is free to evolve on its own terms, according to the simple, fundamental laws of gravity and gas dynamics. This theoretical framework, born from simulations, found its stunning confirmation in the light arriving from the Void Galaxies themselves. When we turned our most sensitive spectrographs toward these faint targets, we were effectively performing a cosmic autopsy on their starlight, dissecting it to reveal the chemical history of the galaxy. The light told a consistent and remarkable story. Void galaxies are, on average, chemically primitive. They are significantly less enriched with metals, the astronomical term for all elements heavier than hydrogen and helium. These heavier elements are forged in the hearts of massive stars and blasted into space when those stars die in supernova explosions. A galaxy that has experienced furious bursts of star formation will be heavily polluted or enriched with these metals. The lower metal content in void galaxies is the smoking gun for their quiet life. It is the chemical proof that they have been forming stars at a slow, leisurely pace, never experiencing the frenetic starbursts that so quickly enrich their urban cousins. They are, in essence, celestial time capsules, preserving a chemical state much closer to that of the early universe. Furthermore, by carefully analysing the different colours of light within them, we can reconstruct their entire star formation history. We can identify stellar populations of all ages, from ancient faint red stars born 10 billion years ago to the brilliant hot blue youngsters born just a few million years ago. This confirmed that their star formation has been a continuous, low-level hum, not a series of booms and busts. They never stopped building stars. They just did so with quiet, sustainable efficiency, and in this we found the ultimate resolution to their mystery. These lonely worlds are not galactic failures. They are not outcasts. They are something far more valuable. They are the universe's pristine control group. For decades, astronomers have struggled to understand the fundamental processes of how a galaxy forms stars and structures itself. But it was always a compromised experiment, because in 99% of the cosmos, a galaxy's evolution is brutally shaped by its environment. It's like trying to understand the nature of a single tree while it's being battered by a hurricane. You can't separate the tree's innate biology from the overwhelming external forces. Void galaxies change everything. They are that same tree, but growing in a sealed, climate-controlled biodome. Here, in these cosmic laboratories, the complicating, messy effects of the environment, the mergers, the tides, the stripping, are almost entirely absent. Here, we can finally see how a galaxy behaves when left utterly to itself. We can watch cold mode accretion happen without it being drowned out by violent events. We can study the delicate feedback loop between star formation and the galactic gas reservoir in its purest form. We can test the fundamental predictions of our models of dark matter halos without the interference of a dozen neighbouring halos. The objects we once dismissed as insignificant footnotes in the cosmic story have now become one of our most crucial windows into the fundamental physics of galaxy formation. Their loneliness is their scientific superpower. Their emptiness is their greatest strength. The questions that had haunted us for so long, how they formed, how they survived, how they fueled themselves, were now answered by a single, elegant narrative. A story of a gentle escape, a quiet life, and a persistent sipping of cosmic dew. They are the ultimate survivors, thriving not through strength and aggression, but through peace and persistence. We had finally understood their past and their present, but in doing so, we unlocked a new set of questions, ones that pointed not to their own story, but to the deepest secrets of the cosmos itself. Now that we knew how to find them and what they were, we could begin to use them. We could begin to ask what these pristine relics, these quiet witnesses to 13 billion years of cosmic history, could tell us about the very fabric of reality. And so, we arrive at the end of our voyage, not with a map of every shadow, but with our eyes finally adjusted to the dark. We began this journey looking away from the emptiness, our gaze drawn, as it always has been, to the brilliant glittering superhighways of the cosmic web. We saw galaxies huddled together for warmth against the cold of eternity, their light a chorus of cosmic reassurance. But we dared to turn our attention to the spaces in between, to the vast forgotten territories of the universe that our theories had dismissed as barren wastelands. We ventured into the great cosmic voids, armed with skepticism and expecting to find nothing. Instead, we found a quiet revolution. We found the universe's most profound secrets were not shouted from the chaotic hearts of galactic clusters, but whispered from the loneliest outposts in the cosmos. What we have witnessed is nothing less than a fundamental rewriting of our cosmic story. The initial dismissal of void galaxies as mere statistical outliers, as failed seeds that never took root, has collapsed under the weight of observation. These are not failures. They are exemplars. They are pristine laboratories, held in a state of suspended animation, preserving a chapter of the universe's history that has long since been erased everywhere else. In the violent, crowded cities of the cosmic web, galaxies are constantly colliding, merging, and being stripped of their vital resources. They are shaped by the relentless gravitational tides of their neighbours. Their stories are palimpsest of countless chaotic encounters. But in the quiet solitude of the voids, we see what a galaxy can become when left to its own devices. We see the slow, methodical burn of star formation, fueled by an internal reservoir of untouched primordial gas. It is a glimpse into a purer, more fundamental mode of existence, an alternate evolutionary path that has now become an essential piece of the puzzle. Without these lonely wanderers, our understanding of galactic evolution would be profoundly incomplete, like trying to understand a society by only studying its most turbulent cities while ignoring its quiet, self-sufficient countryside. The Void Galaxies have provided the control group we never knew we needed, forcing us to recalibrate our models and acknowledge that a galaxy's destiny is shaped as much by what isn't there as by what is. This journey has also led us deeper into the greatest enigma of modern physics, the nature of dark matter. For generations, we built our understanding of this invisible substance by studying its most dramatic effects. We saw it in the gravitational lensing around colossal clusters, bending space-time itself. We inferred its presence from the impossibly fast orbits of stars in the outer rims of massive spiral galaxies, a gravitational anchor holding them together against their own momentum. Our theories were forged in these crucibles of extreme gravity, where dark matter was abundant and its effects were undeniable. But the Void Galaxies have offered us a different perspective, a more subtle and perhaps more revealing one. Here, in these underdense regions, dark matter halos are not the gargantuan, overwhelming structures we find elsewhere. They are fluffier, less concentrated, and more diffuse. This discovery has been a quiet bombshell. Our standard model, the cold dark matter theory, which has been so successful in explaining the universe on large scales, struggles to perfectly replicate these wispy, low-density halos. It predicts a cuspiness, a dense central core of dark matter that we simply do not observe in many of these isolated systems. This discrepancy is not a failure of our quest, but a thrilling new clue. Could it be that dark matter is more complex than we imagined? Does it possess a subtle self-interaction, a faint ability to push against itself that only becomes apparent in these low-pressure environments? Is it warmer, moving faster in the early universe than our simplest models suggest, smoothing out the very clumps that would have formed those dense cusps? These are no longer fringe questions. They are now at the forefront of cosmological research, inspired directly by the gentle evidence provided by these lonely galaxies. They are acting as cosmic particle detectors of a kind we could never build on Earth. By studying their rotation, the distribution of their gas, and the subtle, gravitational lensing they produce on even more distant objects, we are probing the fundamental properties of dark matter. The loneliest objects in existence are helping us close in on the substance that constitutes over 80% of all matter, a substance whose ghostly gravitational scaffolding dictates the very architecture of reality. The void is not empty. It is a testing ground, and its inhabitants are the instruments that are pushing our theories to their breaking point, and in doing so, they have illuminated the grand cosmic tapestry itself. The existence and distribution of these voids are one of the most powerful and elegant confirmations of the universe's accelerating expansion, driven by the mysterious force of dark energy. The voids are not simply passive gaps, they are active participants in the cosmic story. As the universe expands, these under-dense regions expand faster than the dense filaments, acting like rising bubbles in a cosmic fluid. They actively push the great walls and filaments of galaxies further apart, sculpting the web on the grandest of scales. The Void Galaxies, embedded within these expanding bubbles, are like corks bobbing on an invisible tide. Their motions, their subtle drift away from the great concentrations of matter, are a direct measurement of dark energy's persistent, inexorable push. They are the most sensitive barometers we have for the cosmological constant, that strange energy of empty space itself. By finding these galaxies, by mapping their positions and measuring their velocities, we're not just cataloguing oddities. We are taking the pulse of the universe. We are charting the battle between gravity's eternal pull and dark energy's relentless expansion, a battle whose ultimate outcome will determine the fate of everything. The emptiness, it turns out, is the engine of cosmic destiny. Therein lies the most profound paradox of our journey. We looked into the abyss, the symbol of nothingness, and found the keys to understanding almost everything. We have discovered that these isolated galaxies are the Rosetta Stones for cosmic evolution, the purest examples of how stars are born and how galaxies breathe. They are the ghost hunters of cosmology, revealing the subtle nature of dark matter in a way the great clusters never could. They are the cartographers of space-time, their positions and movements tracing the influence of the dark energy that will ultimately seal the universe's fate. It is a humbling and awe-inspiring realization. The objects we once considered cosmic footnotes, the runts of the galactic litter, have become our most treasured guides. They have taught us that to truly comprehend the whole, you must understand all its parts, especially the quietest, most unassuming ones. Their loneliness is not a sign of failure, but a testament to their unique importance. They are cosmic lighthouses, shining in the deepest dark, illuminating the hidden currents that shape the entire ocean of being. They remind us that significance is not always measured in brightness or size, but sometimes in the clarity that only isolation can provide. But this story is far from over. The revelations we have uncovered are merely the first chapter, a tantalizing glimpse into a new continent of discovery. Our journey through the void has been powered by ingenuity and perseverance, but we stand now on the cusp of an era of unprecedented vision. A new generation of cosmic eyes is turning towards the darkness, promising to transform our faint whispers of understanding into a symphony of knowledge. The James Webb Space Telescope, with its magnificent golden mirror, is already peering into the depths of the voids with a sensitivity our predecessors could only dream of. It is hunting for the very first void galaxies, the faintest flickers of light from the cosmic dawn. In these pristine, metal-poor environments, it may find the fingerprints of the universe's very first stars, the mythical population 3, whose brilliant but short lives forge the first heavy elements. Webb is not just taking pictures, it is performing cosmic archaeology, searching for the universe's primordial DNA, which may be best preserved in these sterile, silent vaults. It will analyse the atmospheres of the few planets that might exist in such lonely systems, forever searching for the faintest signs of life in the most improbable of places. Joining this quest is the European Space Agency's Euclid mission, a surveyor of the dark universe. Euclid will map the shapes and distributions of billions of galaxies over a vast swath of the sky, creating the largest and most accurate 3D map of the cosmos ever conceived. Its primary mission is to chart the influence of dark matter and dark energy with breathtaking precision. For our lonely void galaxies, this means everything. Euclid will detect the subtle, almost imperceptible way their images are distorted by the gravitational pull of the invisible dark matter halos that surround them. It will map the precise boundaries of the great voids, revealing their intricate shapes and measuring how they have grown over cosmic time. By cross-referencing this map with the galaxies found inside, Euclid will provide a definitive census of these isolated systems, turning our scattered discoveries into a robust statistical framework. We will no longer be studying individuals, we will be studying an entire population, unlocking the secrets of their formation and their relationship to the cosmic web on an epic scale. And it will not be alone. NASA's Nancy Grace Roman Space Telescope will soon open its wide, panoramic eye to the sky. While Hubble sees a keyhole, Roman will see the entire landscape. It will survey an area hundreds of times larger than Hubble, discovering tens of thousands of new void galaxies in the process. Its immense field of view will allow us to find the rarest and most extreme examples of these objects, the greenest of green peas, the most gas-rich star-forming systems, and perhaps even dark galaxies. Vast, spinning disks of primordial gas that have yet to form a significant number of stars. Roman will create a motion picture of the universe, allowing us to see how these lonely galaxies drift and move over cosmic time, providing a new and powerful tool to measure the inexorable push of dark energy. It will be the ultimate void finder, transforming these cosmic curiosities into a well-understood class of celestial objects, as familiar to the next generation of astronomers as spiral and elliptical galaxies are to us today. On the ground, a new kind of ear is listening to the sky. The Square Kilometre Array, a continent-spanning network of radio telescopes, will tune into the faintest radio waves in the universe, the gentle hum of neutral hydrogen gas. This is the raw, unprocessed fuel from which stars are made. While optical telescopes see the fire of stellar birth, the SKA will see the fuel reserves. In the void galaxies, where this gas has been left largely undisturbed for billions of years, the SKA will create spectacular three-dimensional maps of their enormous, pristine hydrogen clouds. We will see the delicate tendrils of gas flowing into them, the reservoirs that will sustain their slow, steady growth for eons to come. We will be able to weigh their gas content with astonishing accuracy, finally answering the question of whether they are truly inefficient at forming stars, or if they are simply playing a much longer, more patient game than their cousins in the galactic metropolis. The SKA will hear the true silent song of the void, a song of potential, of unspent fuel, of a future that has yet to be written. Our journey through the cosmos is, in the end, a journey back to ourselves. It is a reflection of our own innate, unquenchable desire to understand our place in the grand scheme of things. We look to the voids, these great cosmic deserts, and we felt a sense of existential unease, a reflection of our own fears of loneliness and insignificance. But the universe has surprised us. It has shown us that these are not places of cosmic abandonment. They are places of clarity, of preservation, of fundamental truth. The loneliest objects in the universe have taught us about connection, the invisible connections of dark matter that bind galaxies, the repulsive force of dark energy that drives them apart, and the unbroken chain of physical laws that governs a star-forming cloud in the Bhuta's void, just as it governs the sun in our own crowded spiral arm. They have shown us that even in the most profound silence, there are stories to be heard, that emptiness is not an absence of meaning, but a different kind of canvas. As we stand here, at the edge of this new frontier of discovery, we are filled not with a fear of the dark, but with a profound reverence for it. The great voids are no longer a blank space on our map. They are a destination, a promise of new wonders, a testament to a universe more strange, more subtle, and more magnificent than we ever dared to imagine. All we have to do now is to keep on listening,